Okay, welcome back. Now I'm going to do a problem. I'm calling it block leaving circular track. So I have a block here at the top of an incline, and then the original height is 10 meters. The shape of the incline doesn't really matter. There's no friction here. The friction along the track and the incline is assumed to be zero, so the shape really doesn't matter. You give it a certain initial velocity, and then the block comes and goes around. Right, so I want to find out where does the block, if at all distance, if at any time, when does the block leave the circular track, right? So when does it leave? So let's say somewhere here, right? If the velocity of the block is such that it's too small, what's going to happen? The normal force is going to be zero, and then the block is going to fall at that instant, right? So is there ever a time when the normal force reaches zero, and when does that happen? Let's call this angle here theta. So then what are the equations of motion here? We can say the initial kinetic energy of the block, right, is going to equal to its final kinetic energy plus the final potential energy, right? The initial kinetic energy is half times the mass of the block times the initial velocity squared. The final kinetic energy, half mv final squared, and then the final potential energy is mgh final. And then plus we also have an initial potential energy because it starts up from a certain height. So then we have here mgh initial. And then the m cancels, the mass of the block cancels, right? So then we can put in all the numbers now. We can say 9.8 times 10 plus half. Then the V initial is 2 squared, half V final squared plus, we don't really know at what point it's leaving it, so we have to come up with some kind of equation, right? So this is equal to 4 meters, right? So this height will be what? 4 sine of theta. 4 sine of theta. So the final height is going to be the 4 meters, the radius of the circle, plus the 4 sine of theta, right? So then it's going to be here G 4 plus 4 sine theta. Okay, so then what is this going to be here? The 2 will cancel the 2. And then you're going to have here 98 plus 2. Okay, so this is 98 plus 2. This is going to be 100 is equal to half V final squared plus the 4 can be factored out. 4 times 9.8, right? Then you got here 1 plus sine of theta. Okay, and then we could multiply everything by 2, get rid of this 2 here, so this will be 200, and then the 2 will go over there and we'll make this 8. So we'll just have here V final squared. So this formula, this equation based on energy conservation gives us a relationship with the when it leaves the surface, if at all it leaves it, right? And when it leaves the surface, right, and the final velocity. So we have a relationship between the two, okay? So then the next thing we need to analyze is the forces over here. So the force here is going to be what? So the surface is pushing down on it with a normal force, right? Normal force N, right? And then we have the weight here, mg. Right, so then it's going to be what? We can break the mg into components. This angle is theta. If that angle is theta, then that's going to be the same as what? Because the rectangle looks like, the triangle looks like this. This is the center here, right? So I decided to call this theta, so this is going to be theta. So then this component of the weight, and then we're going to break it into this component of the weight. Right? So if this is theta, that means this is going to be theta. So then this component of the weight is going to be mg cos mg sine of theta, right? So towards the center is going to be mg sine theta. Usually we call this angle theta, but in this problem I call this one theta. So it's kind of up to you what you want to do. If you want to call this theta, then this component of the weight will be mg cos theta, right? And then this component of the weight will be mg sine theta. So in this case, I call this one theta, this one is 90 minus theta, and then this is theta. So then this one will be mg sine theta, and then this one will be mg cos theta. If I call this one theta, then this one will be mg cos theta, this one will be mg sin theta, but then this one will be cos theta. The equation itself will change, you see? So then what's going to happen now? These two forces are towards the center, so they provide the necessary centripetal force. So N plus, right, mg sine theta, right, is equal to what? mv squared, mv final squared over r. So the whole idea is this. You don't want v final to be low, because if it gets low, the normal force is zero, right? So that's kind of what the goal of this is. The faster we make this go, the faster the initial velocity, the better it is for us, because the final velocity here will always be large enough, and you'll be able to safely make the turn. So let's see what's going to happen. If I put here normal force is equal to 0, what am I going to get? If the normal force is 0, m cancel, v final squared is going to equal what? rg sine theta. Okay, and then now we can put that in and see if we get an answer, right? Here we're going to get 200, okay, minus, and then 8 times 9.8 will go to the other side. 8 times 9.8 is going to be 78.4, right? And then we have here 4 times 9.8 plus 8 times 9.8, 4 times 9.8 plus 8 times 9.8 times sine of theta. Okay, so then you have here 200 minus 78.4, 200 minus 78.4, that's going to be 121.6, right? Then that's going to equal, this is 12 times 9.8, 12 times 9.8, so 117.6 sine theta. Okay, so then what's going to happen? Sine of theta is going to be equal to 4. Okay, so what does that mean? Can the sine of an angle ever be greater than 1? No, right? So what does that mean? We are safe here. That block will always stay on that track. Okay, no matter what happens, it will always stay on that track. Now, what if the initial velocity was 0? Is that going to change anything? Let's say I let it go, initial velocity 0. Is that going to help our case? No, it's actually going to make it worse, right? Yeah, it's going to make it worse because the final velocity might end up becoming a little bit smaller, and it might actually end up dropping off. So what will happen if the initial velocity was 0? This will disappear, and instead of 9.8 times 10, you're going to have just 98. And then remember, this one added 2 to it, we got 100, so it's just going to end up becoming 98. And then 98 multiplied by 2 is going to be 196 here. 196. So if the initial velocity was 0, let's see what's going to happen. Now it might actually fall off. Right? So if we have 196, what are we going to get? 196. The rest of everything else stays the same. This v final squared equation stays the same. It goes in here, right? Then it goes in there. This one stays 117.6. Now 196 minus 78.4. $117.6. 117.6. And now sine of theta is 1. Okay, so what does that mean? Theta is 90. Oh, what happens? That means this thing actually makes it all the way to the top. Very interesting, right? This thing makes it all the way to the top and then falls off. So if I let it go with an initial velocity, remember this one was 10 meters, right? If I let it go with an initial velocity of 0, then it comes down, it's safe, it's safe, it's safe, it's safe, it's safe. When it goes over there, it doesn't stop. It has a certain final velocity, but it's going too slow, and it's going barely at the minimum velocity. So at that point, it might actually fall off. So if we wanted to find out what the velocity there is, what would that be? V final squared is equal to, what was the equation? it was Rg sine of theta. So this is equal to V final squared is Rg. So this is actually the equation that we derived for the minimum velocity at the top of a revolution type ride. This is V min, square root of Rg. So actually this block might still be on the verge of being safe. It's still traveling, the normal force reaches 0, it's about to fall, but it actually still, since it's going, it kind of is safe and it makes the turn, barely makes the turn, okay? So then, in other words, for this height and for this radius of 4 meters, we're still okay. Okay? Even though we're saying it kind of might fall off at the top, I think it's still okay. Now, what are we going to do? What if we have the initial height a little bit lower? Or what if I change the radius of the circle? So either making the radius of the circle larger or making the original height lower is going to cause you to be more of a danger, right? So then what's going to happen? What if the original height is 8, right? And you give it an initial velocity of 2. So let's see how that will change. So let's say the initial height is 8, and then now the initial velocity is 2. This equation still doesn't change, the V final squared equation. That stays the same. This just part changes. So instead of 9.8 times 10, you have 9.8 times 8. Then you have half of 2 squared, right? So then this will cancel. 9.8 times 8 is going to be what? 9.8 times 8, that's 78.4, plus you're going to add a 2, right? So 78.4 plus, you're going to add a 2 to it, right? And you're going to get what? Plus 2, you're going to get 80.4, right? That 2 is due to the kinetic energy, right? 80.4. Then remember, I multiplied everything by another 2, right? Now that's a huge, huge difference. Now this block is going to fall off somewhere here. It's not even going to make it all the way up to the top. No way. It's definitely going to fall off. So instead of 200, we've got here 160.8. 160.8, right? Then you got the 9.8 sine theta. That doesn't change. This one, you still got the same, right? So I kept the radius of the circle 4. So you got 4g sine theta. Then the 9.8 goes over to this side, and now we have here 160.8. 160.8. Now 160.8 minus 78.4. That's going to be 82.4. 82.4. And now this side doesn't change, 117.6, and now actually falls off. Definitely falls off. So now we have 82.4 divided by 117.6. Okay? Then we take we get 0.70. 0.70068. Right? Then we take the inverse sine of that. We get 44 degrees. Theta is going to be 44.5 degrees. Okay? So then what's going to be the final velocity? Then the final velocity, you can put it in here and you can actually calculate it. It's going to be R times G, so 4 times 9.8 times sine of theta, which was 0.70068. 0.70068. Then you're going to multiply all of that and then square root it. So sine times 4 times 9.8 and then square root that. We're going to get 5.24. V final is 5.24 meters per second. So the conclusion of this problem is this. The picture looks like this. Okay, so then you got here, this block is starting 8 meters up. It's starting with an initial speed of 2 meters per second, right? Then it's going to come, this is 4 meters radius. If it's 4 meters radius, that means the top of the circle is same as the top of the incline. You see, 4 meters radius. So it's going to be like this, 4, another 4, It looks like this, you see. So then this is going to come down like this, and how far up is it going to make it? Okay, the angle is 44, so that looks something like this. So it's going to make it all the way to over here. How fast is it going? It's going 5.24 meters per second. Why is it going faster than what it started with? Well, because it's lower. It's lost potential energy, so it should be going faster, but it's not going fast enough. So at that point, the normal force is 0. So the only forces on it at that point are what? mg. When the normal force cancels, you got the force is mg. So the mg breaks into two components, this component and this component. And this component of the mg, which we called mg, this angle was theta, so we called this one mg sine theta, right? So this component of the mg was sufficient to equal to its centripetal acceleration. Mg sine of theta was mv squared over r. Well, because the velocity was not fast enough, what ended up happening, this equals this, and you don't need a normal force. The normal force drops. Whenever the normal force drops, that means the block is no longer touching the surface. The surface does not need to push on the block inward. If it doesn't need to push on the block inward, that means it's going too slow. That means the block just falls off due to the gravity of its weight. So what is its trajectory going to look like? This is kind of an interesting question. What is its trajectory going to look like? Well, its trajectory is going to be the same as once it kind of leaves the surface, it's the trajectory that is given by projectile motion. It's the initial velocity is this way, right? What is the initial velocity? 5.24, right? So then it's going to go like this. Gonna go like that and then hit somewhere here, you know. So it's hit somewhere on the incline. So it's basically a projectile motion. We can almost break this up into a second question and say, okay, the block is moving like this. So it kind of acts like a block on a hill problem. The block is moving like this. It's moving at 5.24 meters per second. Then you can break the velocity into two components, right? And then do a projectile motion problem, go like this, right? If this one was, if the inclined plane wasn't there, if this one was going like this, let's say it was going like this, and it was going like this, and then the circle, right? So then the block would have been here, it would go like this, it would go like this, and then it go like this, and then hit the ground somewhere, right? But if they're kind of close to each other, then it's going to go and hit the inclined plane somewhere. So we can take its velocity, break it up into components. Well, what is this angle? If this angle is 44.5 degrees, right? Then what is that? Let's see, this is 44.5 degrees. This is like this. We want to know this angle. So if this is 44.5, this is 44.5. This one is the complementary to 44.5. So it's 45.5. So this is 45.5 degrees. You break that up into x and y components. So the initial x equals 5.24 cosine of 45.5. The initial y is 5.24 sine of 45.5. You already know the distance, the original height, right? That's going to be 4 plus 4 sine of, so this is the original height here, 4 plus 4 sine of 44.5. This is h initial. And so now it becomes a projectile motion problem, where the problem can say, well, where does it land on the flat surface? The flat surface is an easier question, right? And then you can say, oh, okay, it lands on the flat surface a certain distance away from where it started, okay? So you can see how you can combine several topics here from circular motion, energy, the normal force going to 0, then it's going into projectile motion, and then where does it hit on the ground, okay? Thank you very much.